Thank you, Marjorie. Thanks for the introduction. Also, thank you for organizing the session. It's really great. So, the title that I gave, when they ask you for these titles and abstracts, you give something vague, so it can be anything. So I called it Model-Based Approaches Towards Assessing Dynamic Connectivity. After I was done, I sort of changed it to Investigating the Impact of Autocorrelation on Time-Varying Connectivity. But it's a little bit of both. But that's sort of the general idea. And so if you've been walking around, the meeting or going through the poster session, you see that this sort of time-varying or dynamic functional connectivity is all the rage right now. And so there's a lot of really interesting results and findings that people have. However, there's still some sort of questions that remain whether or not a lot of these fluctuations that people are seeing are important or dependent on sort of physiological compounds and the like. And so, since we're going to be critical here, I want to investigate some of these things. And in addition, there are also some outstanding questions about sort of the optimal techniques to use it when analyzing this type of data. So in this talk, I'm going to describe some of the benefits of using a model-based approach towards assessing dynamic connectivity. And this is something that I've been talking about a few years, and I think I did it on a similar stage a few years back. And I'm going to show how using such a model-based approach can sometimes tell you a little bit about the problem and illuminate sort of necessary assumptions that need to hold so that you don't get sort of spurious dynamic connectivity. And I'm also going to take these assumptions and put it onto sort of more standard approaches like sliding windows and show how if you ignore these assumptions, maybe bad things can happen. Okay? So, the most widely used technique, and if you were here this morning, there was an excellent symposium on dynamic connectivity, and they went through these things very carefully, so hopefully you saw all those things. But the most widely used approach is the sliding window technique, where you took a time window of fixed length, and you calculate the correlation within that time series window and just move it along. And that gives you sort of a time series of the correlation across time. And so sometimes a tapered version of the sliding window is used instead, and that's what I'm illustrating there. And then sometimes people use these sort of k-means clustering approaches as a secondary step to sort of determine different brain states and the like. And I'll illustrate that later on. And so one of the things we want to determine is, well, how good is it using a sliding window, and what's sort of the sort of natural variability involved when you use a sliding window technique to analyze your data. And so what statisticians often use to look at how good an estimate is something called the sampling distribution. And so the sampling distribution tells us what values can this statistic that we're estimating take, and how often does it take those values. And so for a correlation, and so this is, I'm showing here to the what is it? Is it left or right? I don't know. It depends on what side you're on, who you're facing. But the little bell curve over there, it shows you this empirical sampling distribution for a sliding window of length with width 30 time points. And so the standard deviation of this is roughly 1 over the square root of the window length, which is about 0.2 or something like that for a window length of 30 time points. And, it's roughly Gaussian. So Gaussian has some nice properties in normal distribution. So roughly, 68% of all observations are within 1 standard deviation, 95 are within 2, and almost all observations are within 3 standard deviations. So that's plus minus 0.6 in correlation units. And so basically, I think this is a good way of looking at the problem. So what is this? What is it we're doing in sliding windows? Well, basically what we're doing is we're repeatedly sampling from this sampling distribution. Now, it's going to be sort of correlated because the sliding window are highly correlated with each other. So if we're sampling from one side of the distribution, we're going to be more likely to sample from that side the next time. But basically, as the time progresses, we're going to travel through this distribution and sample time points, basically ranging between minus 0.6 and 0.6, with most of them, 68% of the observations within a 0.2 of 0, in the null case. Okay, so this is all for the null case where there is no true sliding, no true time-varying correlation. So what I'm trying to illustrate here is that even if there's no correlation, it sure does look like something very compelling, because it's sort of going from, negative 0.5 to 0.5 in this smooth way, and it looks like something really interesting is going on. But this is just what noise looks like for a sliding window of this length. Now, how can you make this less of a problem? Well, you can make the width wider, and that's going to shrink the sampling distribution. If you go in the opposite direction and maybe only do 15 time points, it's going to get much, much, much wider. Okay? And so then these null distributions are going to be all over the place. All right, so that was sort of an interesting, and this is a problem that we thought about a lot a few years ago, and so we defined a sort of a model-based approach for dealing with this, and we call this dynamic conditional correlations. And this comes from the finance literature, and this is what's called a multivariate Garch model. It's not a pretty acronym, but it's called Generalized Autoregressive Conditional Heteroscedastic Model. And so basically what you do is you first sort of model the data, say the data is this, say maybe it's a normally distributed with some time-varying variance, and then you do a model for how this variances change over time, and then you have a component that calculates the time-varying correlation. And it does this in an adaptive way. Now, it looks very, very ugly, but it's actually quite efficient. And so, we showed this in a paper from 2014 that, in general, what happens if you have the same null data, the sampling distribution is much shrunk. So you'll see them on top of each other. So there's a sliding window with length 30, with width 30, and then the DCC is below it, fit on the same data, and you'll see that it's much, much more narrow around 0, which is the true value in this null case. So what's going to happen here is you're going to be much less likely to be sort of tricked and think that there's sort of compelling evidence, because it just, if it is a null case, it's not going to sort of trigger this. And so we were really pleased with this, and so we thought we'd solve the problem and call it a day. And so we made the code available, and then people started asking some questions, saying like, well, in this case it doesn't work, and that was a little discouraging, but that forced you to sort of go back and say, well, what was it that didn't work, right? And so the nice thing about the model-based approach is that there's some assumptions that are built in. And in particular, the assumption, I want the first equation there, because, I really want you to look at these messy equations. But on the first one here, basically what you're assuming is that the data is IID. That means that there's no sort of temporal correlation in the data. That's intrinsic in this model, but that's not intrinsic in fMRI data. And so that's something that we quickly saw that the people that were having trouble, it was probably due to this fact. And so DCC assumed that the data is independent with 0 mean. However, we know that fMRI data is autocorrelated. For sort of standard 2-second TRs, the autocorrelation, the lag 1 autocorrelation is roughly 0.3. But, with these modern sort of HCP types of acquisition, they get even higher. And so what we realized is that we needed to incorporate sort of an appropriate model for the autocorrelation as well. And so oftentimes in sort of like your GLM model, when you fit a GLM using task-based fMRI, you use something like an ARP or an ARMA11 in the GLM. And so we decided to do something similar for that. And then, of course, if you have, you need higher order AR processes if you have a higher temporal resolution. And so what we did is we introduced the following concept, is that we actually put here's an AR1 DCC, where we sort of modeled this as an AR1 process rather than an IID process. And so what happens then is it seemed to sort of fix a lot of the problems that people were having. And what you'll see here is on the top is sort of the sampling distribution for DCC when there's no dynamic connectivity, but there's an autocorrelation within each time series of 0.3. Okay? And so what you see is that the sampling distribution is a little bit wider, so you're starting to get like things that look more like spurious correlations. It's not as smooth as in sliding windows because it's done in a different manner, but it looks like there's a lot more variation going on. However, if you do this sort of AR1 DCC, it gets rid of it, and that's that red line there. So it's basically not being fooled in the same way. So the interesting lesson here was that we found out that there was some problems with the method. Because it was this model-based approach, we were able to go in and see, well, which assumptions are violated, and by doing that we realized that this autocorrelation seems to be really important. And so what we did, and so this seemed to solve the problem for the DCC approach. But then the question is, what happens in a sliding window approach? And so that was the next natural question, is like, well, if this assumption is so important for DCC, it stands to reason that it might actually have some impact on your sliding window correlations as well. So how does autocorrelation within a time series affect the results of a sliding window analysis? And the surprising thing is, well, it was surprising for me at least, is that increased autocorrelation within a time series, within two independent time series, will inflate the dynamic correlation between two different time series. So just, if I have two time series and they're uncorrelated with each other, so the dynamic connectivity is 0, if I make them more autocorrelated with themselves, the dynamic connectivity is going to look much higher. Okay? That seems a little bit counterintuitive, but it turns out to be true. And here's just a sort of cartoon of this. On the top row, there's no autocorrelation in the time series. So these are just two IID time series that have no sort of dynamic in none of the three cases is there any dynamic connectivity between them. But in the first case, they're just IID, and you get a sliding window like the one on the top right there, you know, that's sort of just noise. And if you increase the autocorrelation within each time series to 0.4, it starts looking a little bit more like dynamic connectivity. And if you make the autocorrelation up to 0.8, so you make these things really, really smooth, what's happening is the dynamic connectivity is sort of wandering between 0.8 and negative 0.8, even though they're not completely uncorrelated with each other dynamically. It's just because they're correlated with themselves. So this is a sort of spurious dynamic correlation in these sliding window that's given rise by autocorrelation within the time series. So this seemed awfully puzzling to me, and so we had to go back to the literature, and we had to go back to 1935. There's a sort of a seminal paper by Bartlett in the stat literature. And so Bartlett said for if you have two time series that are completely uncorrelated with each other, and they each follow an AR1 process with some parameters phi x and phi y, then basically the variance of the correlation is going to depend on those phi values. And so what this shows is that the phi values get bigger, the variance increases. And what happens when the variance increases? Well, this sampling distribution gets wider and wider and wider, right? And so basically you're just going to transverse this sampling distribution, and you're basically going to find a lot of spurious results. And so this sort of led us to believe that perhaps we need to do some sort of pre-whitening of sorts of the data prior to doing sliding windows. And so here's a little bit of a cartoon showing the sampling distribution for null data as a function of the autocorrelation parameter. So you'll see when phi is equal to 0, it looks like the normal thing. And then as phi is equal to 0.3, it gets a little wider. And then at phi equal to 0.6, it just sort of explodes and gets really, really wide. And so you're going to get really, really high correlations and really low correlations, even if there's nothing going on, if there's that much correlation in your data, which it might very well be in sort of HCP type acquisitions when it's 0.7 or something between the TR. So this is potentially quite important. So we did a couple of simulations to sort of address this issue, and these are simulations from our 2014 paper, but we just redid. I don't have that much time, so I'm just going to sort of show you the highlights. And basically, this is what's happening, is that in each of these cases, this is null data, and we're looking at how much variability is there in the data. You know, how big of a dynamic connectivity are you going to think that there is in these null data sets? And as you see in the green there, as the autocorrelation within each time course increases and goes towards 1, it's going to blow up. And you're going to say, well, hey, there's an awful lot of compelling stuff going on in this data, when it really is just not there. It's spurious in this case. And what you see here in the orange is that this is taken care of if you first pre-whiten the data. So if you pre-whiten the data, remove the autocorrelation, and then do sliding windows, it seems to work much better. And so here's similar things when you actually have a dynamic connectivity, and it shows that if you pre-whiten it, you tend to estimate the true dynamic connectivity better even in this case. And so this would seem to be very these simulations that we did seems to encourage the fact that you need to sort of compensate for the autocorrelation and sort of remove it prior to doing these sort of sliding window analysis. Otherwise, if you have really highly correlated data, it's going to look like you have a very strong dynamic connectivity when in reality there's really nothing going on. And so this is a little bit troubling. And so the question is, well, how does it impact sort of the analysis that people do? So oftentimes people do these sort of sliding window techniques, and then they do k-means to find these sort of distinct states, right? And so we did a reproducibility study of it, and this is work by Ann Cho and a lot of other people in the room here that I can see. And so I took the data that we used in that one, which is basically, it wound up being 21 different signal components that were signal nodes that were derived from using ICA, and we had test-retest data. And so basically what we did is we did a sliding window with and without pre-whitening, and then we did k-means. And we did this on the test-retest data to see how different they looked and how reproducible the results were. And so, and this is sort of the Vince Calhounian method of doing things, so I'll put that up there as well. And so here's basically the results, and as you'll see, these are the two sort of states that we get in session one. And on the top is when it's non-whitened, you know, when you have this autocorrelation present, and in the lower it's when it's pre-whitened. And as you'll see, they look roughly the same, but the pre-whitened looks a little bit lower. It's not as sharp, perhaps, if you're looking at that. Now, if you look at session two, you'll see that they're remarkably reproducible in each case, which is sort of nice. But the interesting plot, I think, is this one, which is sort of the difference between the pre-whitened state and the non-pre-whitened state in these two sessions. And again, it's very reproducible, the difference between these two things. But the difference is quite big. If you look at the legend, it's ranging from maybe negative 0.4 to 0.4 in correlation values, which is quite big, right? So this is over 20 subjects. And you'll see that there's also a pattern that there's certain relationships that between certain networks that are particularly impacted by that, because you can sort of see a banding factor in these errors. And so to me, this is seems very concerning and something that I think we have to take quite seriously. And so that's sort of one of the things that I want to highlight in this talk, and sort of I want it to be critical, because this is critical perspectives. And so I'm not saying that everything is garbage or anything like that. I'm just saying that I think this is something that we should take seriously, and it seems like something that could potentially fool us into thinking that we have more compelling results than we really do. And so, in conclusion, I'm actually going to finish on time. I have 45 seconds. All right. So the focus of resting state fMRI, has shifted a lot from static functional connectivity to the analysis of dynamic functional connectivity. And so, although a number of studies have reported compelling results, there's still, various shortcomings of the regularly applied approach. So there's been these shortcomings that we've talked about in sliding windows, that the arbitrary window length and something like that. I want to put a new thing on your radar, that the autocorrelation within the window is really, really important. Okay? And here we discussed the benefits of using a time series approach to assess dynamic connectivity, because it was because I used this model-based approach that even came on my radar. So I'm going back to my original titles. I said I was going to tie that in. And we also discussed the importance of modeling autocorrelation present in the data. So there's a lot of people who have worked on these projects in the various, so Jessica Cohen is there, Ann Cho, Heather Chappell are all here, and they've worked on numerous of these things. And so I was putting up all the dynamic connectivity work that we've done, and it's adding up to a lot. So this work is based on the middle one with Hamed Hanari, investigating the impact of autocorrelation in time-varying connectivity, which will hopefully be on archive within a week or two. And I'll also do a shout out to Heather's poster. It's at the very end. I don't know what the poster number is, but it's on using hidden semi-Markov models. And so I want to thank you for your attention. Thanks.